Hey everybody, this is Larry. This is day 18 of March. Leetcode problem, hit the like button, subscribe button, join me on Discord, let me know what you think about this problem. I struggled a lot with this problem. You could look at it by the length of this video. And on videos where I think it goes for too long, I actually re-record like a short explanation in the beginning so that you don't have to skip ahead too much. Though you can watch me sub live, and actually I took a really greedy path that was wrong, and you can kind of see how I got there. I don't know why there's this like bar on the bottom. That's why I refreshed. But awkward. But yeah. So this is Wiggle Subsequence. It's a problem that I struggle with, though. It's not that hard of a problem according to Leetcode difficulty, but sometimes you just have bad days. Also, I need sleep. It's 4 a.m. That's why I've been posting these videos late lately, because I've been sleeping at a normal-ish time. But today I did not. But for this problem, the key thing to note is, and I'll go over the code in a second, but for now we can focus on just this thing. The key thing to note is that well, there are a couple of observations. The two big one I would say is that there are only two types of wiggle subsequences. Basically, one that goes up, down, dot, 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 or down, up, dot, 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 right? So here, once we have a strategy, we can just brute force whichever one. And then let's say, for the symmetry reasons, because the other one just is the same pretty much, at least the proof wise, we can try the up, down one, right? Well, what does that look like? Well, up, down, up, and then down, and up, and then down, and then up. Well, the thing is that with these sequences is that you can always, the idea is that you have a sequence of increase. Let's say you're looking for an up and you have a sequence of up like this, right? Well, what happens is that you actually only want the two numbers from here, from this longer sequence, 5 and 15. And from then, and in a greedy kind of way, you always want to take the biggest number on this uphill slope, right? Because it doesn't ever make sense to take the 10. It doesn't ever make sense to take the 13. It always makes sense to take the 15, given that we have this sub list, not to be like this contiguous this contiguous sequence. You always want to take the max, and as a result. Another way to phrase it is that if you're going up adjacent numbers, you only want to take the max, which is when the direction changes. So basically now you're changing this problem to counting the number of directional changes. And with that, that's how you could do it in linear time. So I spent a lot of time because I was trying to do the linear solution on the explanation. The n squared time I actually go over really quickly in the video. So if you're looking for that, just keep on watching, and I go over it, the couple of instances like really quickly, and then I jumped into the O of n times. But yeah, so now that we kind of reduce this by, you can think about this as compressing it and just deleting everything in the middle. 15, 10, 5, well, we don't need the 10. And then we go 16 and 8, and this is our answer, right? And then again, we just brute force check, on a sequence, and then just check for the other possible one, which is the same idea, and then just kind of see which one is longer. And then after that, it just becomes implementation. I actually initially thought it was going to be dynamic programming so I actually implemented top down, but you can kind of roll that up to a for loop, especially now that you have this formulation of what I just said about looking at adjacent elements, and then just keep on going up until you can go up, and then go down, and then so forth. So it becomes a wiggle sequence becomes counting the number of peaks and valleys. Yeah. which is kind of a funky way of doing it, but it's true. So then, and even though this actually does not need memorization, so it's not really dynamic programming in that sense, you can actually, use this practice for us as a formulation for how to think about things recursively and for transition purposes. In this case, we actually didn't need it, but it is a good practice, and actually, I did not mind that at all. So as we said, so this is just, let's say we find in the next increasing, or we find in, so we have two functions. We want to, for this one, we want to answer the question, find the longest wiggle sequence where the next direction is increasing. And then the other one is the opposite, where we find the longest wiggle subsequence where the next direction is decreasing. And then here, we just go for the base case, with indexes at the last element, then we return 0. If this is the first element, we just return 1 because that's going to be in the list. And then you continue to find the increasing element, right? Starting on the next index. And then after that, if this is still increasing, then we keep on going because we want to find the next peak, if you want to call it that. But while it's increasing, you want to find the next element that's increasing. If this is no longer the case, meaning that if the num sub index is now decreasing, then we just now able to return 1 plus to find the next decreasing element. And there's some symmetry in the find decreasing part, and that's basically the idea. For the time complexity analysis, also, wait, before I do that, notice that this in structure is actually very familiar to the problem that we did 2 days ago, best time to buy and sell stock. So that's why I would urge you to kind of practice thinking about it like this as well, so that if you did need memorization, then you could do that. But in this case, note that for every input to index, we don't have any branching, right? We only look at the next element. So index is always going to look at index plus 1 and only one possible outcome, right? So in that sense, because we don't have to make any decision, we always return directly. We don't actually have to memorize because it is essentially a for loop in a funky way. And as a result, this is going to be linear time because the possible index is going to be 0 to n. Each of them does all of 1 work. And as a result, this is going to be all of n time in total. And it's going to be all of n space due to the stack space in total. Cool. That's pretty much all I have. This is tricky for me. I think it's just because I missed that observation in the beginning. You could watch me struggle for the next hour if you like, before I finally got it. But yeah, let me know what you think about this format, because sometimes I do mix it up a little bit. And let me know what you think. Yeah. Hey everybody. This is Larry. This is 18th of March. Hit the like button, hit the subscribe button, join me on Discord. I'm really sleepy. That's why I've been not doing these earlier, but today, I don't know. Dubious mistakes maybe. Okay, today's problem is wiggle subsequence. Hit the like button, hit the subscribe button, join me on Discord. I usually stop these lives, so if it's a little bit slow, just fast forward, give me comments, whatever you like. Okay, so what is a wiggy? Wiggle? Why did I say wiki? Wiggle? Wiggle subsequence. Okay, return the link with the longest wiggle subsequence. Yes. Yeah. Actually, it's really funky. Okay, so basically you want a sequence that's going up, down, up, down, up, down. Can you solve this in O(n)? Of course. I guess n squared is very obvious. Wait, see subsequence? I guess n squared is very obvious in just like you could do dp or something like that. It's not that obvious, but it is like a naive dp on the index and up or down, and then maybe you can do that without it anyway, huh? Maybe that's it. Maybe that is actually. No, that's still n square. I mean, some of it you can even depend on how you want to say it, because you can take advantage of the fact that each number is less than 1,000, and then but that's still n square ish, or at least 1,000 square ish. If you do a DP. So how do we get this in linear time? Even though I guess this is the follow-up, but I think it's not that interesting, maybe for me anyway, to get the n squared dynamic programming. I think the n squared dynamic programming state is, you can do this in a number of ways. One is just the index and whether the last number direction is going up or down, and you can also do that on the range of the numbers, which is also up to 1,000, and then also up or down or index and something like that. So you can play around there. N squared is pretty okay. The question is, can you do this in linear time? My guess, if I have to guess with linear time, is, and this is maybe a little bit cheating in the sense that it's kind of like you look at a complexity and you kind of work backwards to kind of see if there's a solution, and assuming that there is, because there's the follow-up. I might think about, the only two things that I, usually come to mind with the subsequent stuff is usually either a queue or a stack. And like I said, it's a little bit cheating to kind of work that way. I think what my usual workflow is to kind of see if I could ask or answer a question in a better way. But yeah, and I suspect that it's possible that it's going to be one of those, like either mono stack or mono queue or something like that. So basically the idea for me is, okay, given this 10, right? Yeah, given this 10, what is the previous number that is bigger than it, right? And then you could ask both questions, which is, given this 10, what's the previous number that's bigger than it? And then that would kind of get you that mono stack. And then you could kind of stores the solution on each one. I think that's roughly it. I know that I'm not explaining it that well. I think I'm still just working through the solution. But I would say that with mono stack or mono queue, in both cases, it's about asking the right questions. And I think the right question for me is, okay, given, let's say, an array of numbers, and this is not a good to be done, array slippy. Let's say you have this array. We look at a given number, and then you ask yourself, okay, there are two questions that you could ask. What is the longest length of a wiggle sequence that ends here, where the last direction, I was going to say operation, but direction is up, and also direction is down, right? So we asked those two questions, and we can solve that, I think, with just a mono queue from that. And then I think that should, mono stack. I mean, I call it mono stack, but it actually, like, I've been saying mono stack because I've been having a lot of practice lately, or maybe not lately, just in general, maybe not that lately, but it actually is just a stack where it turns out to be monotonic, like as that property that way it is monotonic. But I think what the more important focus is that you use a stack, right? And I'm gonna, because basically, let's say you try to figure out what is the last number. Let's say you have a stack, right? And this is how I ask it usually for monostack, which is that, okay, let's start from the beginning. Let's have 1, right? And let's ignore the wiggle part for a second and just keep on asking ourselves, what's the last number that is bigger than this number, right? Well, if it's 1, it's just 1, and then you have 17. Well, 17 is bigger than 1. So what does that mean, right? That means that all the numbers that are to the right of 17, there are two scenarios, right? To the right of 17, let's say we have a number that's smaller than 17. Let's say it's 12. Well, if this is 12, then 17 is going to be the biggest number, or sorry, the next number that's bigger than 12. So then, then 1 will not be the answer. And then the other way is bigger than 17, so let's say it's 20. Well, if this is 20, 1 will also never be the answer, right? So in that case, we can pop up the stack. And that's kind of the invariant of the problem. That's the kind of how I think about these problems. And then, as you kind of you go 5 is good. And then you have 10 pops to 5. And then you have 13, which pops to 10, and so forth. And then as you kind of look at it that way, as we kind of keep on popping smaller numbers, you'll notice that it is a monotonically decreasing stack because of the thing that you're doing. So it's a result of the operation you're doing, and not necessarily that you're going, you're looking at a problem and be like, oh, let's have a mono stack, right? The way to think about it is, okay, there's this property that we want that's invariant, right? Invariant here is that the top of the stack is the next number that can be a candidate. And maybe part of that is also that the entire stack only contains possible candidates, right? Because at any time, this 5. At any time, these are all the possible candidates, right? All the other numbers that are in between, like 13, it cannot be a possible answer for numbers to the right of the 5. And that's basically what the invariant is, and that's what we try to do with these stacks. But yeah, and so all that being said, let's create the answers. Let's just say, okay. Let's see, right? So that said, this is a little bit tricky putting it together. But these are the ideas, and these are the building blocks that as long as you understand that, you can work out the rest. Maybe slowly, maybe quickly, depending on how much you practice. But these are the key points for this problem. And I know that took me a while to get there, but this is not that easy, I would say, for me anyway. So yeah, so now I have 2 stacks. Let's just say big stack and smaller stack. Maybe call it bigger stack just to be consistent. So bigger stack, that's what we know is contains numbers to the left that might be bigger than this number. And then this is the same, contains numbers to the left that might be smaller than this number. Maybe next number is a better way to phrase it. But yeah, so then now we just go through the, and maybe we just have answers. Well, answers up and answers down. Why does it go that way? So yeah, and this is, the best answer where the last operation is up, or last direction. I keep on saying that up. And there, okay. So now we have these things together. We can go, okay, now we could go through the list one at a time. So for x in nums, I just like writing x because it's consistent for me. It's a one level thing. You can probably, use a better number, right? Let's go through it. And this is very tiring because it's just going for the scenarios, which is, okay, let's just say, just making sure that, okay, what is the best answer where this number is the last. I mean, I think this is just this question here, right? So okay, maybe I'll just copy and paste because I'm right. So yeah, so if the last number is up, you want to look at if the last number is going up, you want to go down, so that means that the previous number that you look at will be bigger, right? Next direction is down, or this direction. Next direction. The next direction we're going to do is down, which is this direction that we're going to do, which means we're looking for a bigger number. So here we use the bigger stack, right? So biggest if length of biggest stack is equal to 0, then what do we do? Well, then we append this to the biggest stack, or we append x to the biggest stack, because now this is the biggest. No, I guess the way that I usually do it is while this is greater than 0 and biggest stack of -1 is smaller than or equal to x. Does it have to be strictly smaller than? I guess so. Eventually, I'll lose it. What? No. Okay, I think it has to be non-zero. So yeah, for equals, then we remove. So actually, we have that pop, and then at the very end, we do we put it in. But before we do that, I guess we want to check answer down is equal to. Well, we have to check first if the length of the biggest stack is 0, then we append 1. That's basically a base case. The 1 is just the number that we have now. Otherwise, answer down append. How do we store the biggest stack? Maybe we have to store one more thing on the biggest stack. But basically, biggest stack, the top number, that plus 1, say. And now, yeah, it contains number. And maybe the index. Yeah, let's do the index. Basically, we just have to keep. I mean, we're storing the number, which is fine, but we actually have to store one more thing so that we know what to look up. And basically here, let's just say let's set this to 0, and then here, this is the index. So we want the answer up of there, right? Because basically this is the index of the top of the stack, and then we look up, you know, the previous answer where it is answering up is there, and then here we put in the index, which we have to do by making it enumerate. I'm really tired. Usually I'm a little faster, but yeah, but that's basically the idea. And then we can do the same thing for the for the other side. So yeah, basically we're looking for a smaller number because, you know, like we can ask ourselves the same question just to be sure. What is the longest thing where the last number is up? That means that the next direction is up. If we're going up, we want to look for a smaller number, right? So that's basically the idea here. This may be wrong actually, because I think I mean, this is conceptually right, but it doesn't give us like I'm not actually I'm unsure that this gives us the right answer. It gives us well, at least I have to think about how to prove this, because what happens is that we have a stack of these things, but we actually want to we have to prove a property that I have to figure it out in a little bit, because basically the thing that I'm thinking here is that, okay, right, you know, let's look at this bigger stack for a second. Bigger stack could contain something like and I'm instead of doing the index, I'm going to do the best score, right? Like, you know, it could be something like whatever. We know that it's going to be a decreasing sequence, or it's going to look like that. but it's not clear to me that given this sequence, that the results for this, the longest length, it's going to be strictly increasing, right? Or strictly decreasing rather, because you can imagine that this is, maybe this actually has a longer length if we want to connect to the 12 instead of the 9, right? But it may be that that's not the case, but we would have to prove and convince me of that. So let's play around that, or keep that in mind, and then let's kind of let's finish typing this and then kind of play around with some ideas, some cases for this. Yeah, and then now we just return the max of ends down, ends up. Let's see if it works first. Okay, so it works on that one. Wish they have a press a button to do all the test code one, but I guess it's fine. I think there is an assumption that I made that I'm not proving, and I'm a little bit skeptical about it. So we'll see if these kind of tells us suss that out first. Also, we definitely print out the wrong thing. I didn't notice it the first time, obviously, but yeah, this is clearly wrong, right? I mean, we kind of saw it here. It seems like the linear solution will probably have one more thing. And this is going up, this is going down. This is one, that's good. Wait, I go down first, up first? Okay, down, right? And then here, why is that? Did I mess something up? No, so the up score the up score here should be a 2, but it is not. So the smaller stack should be 0. Up is 0 to 1. That sounds good. Oh, I forgot to push the smaller stack. So okay, so that is an obvious mistake. I think I was just too focused on the possible bug that we were talking about that I didn't get it. Okay, so that looks good. I'm going to print the, but as I said, I'm not convinced that what I said is correct, or that this code is correct. But how do I prove this? That that the best value is strictly decreasing. Right. I guess it makes sense actually, because in a greedy kind of way, the number, you always want to connect a number to the number that is immediately, because you always eliminate because there's no choice, because you always pick the number that's closest to you, which by default will give you the max answer. And as part of the stack, and you can, and if you pop additional 1, it can only, well, okay, I guess I could prove it by scenario analysis. So I don't think I'm going to necessarily do that, but the idea is that you could prove, you just go for the scenarios, which is kind of what I've been doing in my head, where if you have maybe something similar to this, where if you have a 10, or you know, you have a sequence that's like, I don't know, let's just try 15, 10, 15, 10, 5. You know, we have and let's just say here, you know, you have some answer. You know, this is the length of the longest thing. And I think you can kind of maybe prove that this is not possible because by definition, if by definition, every number that's here will have will be using the top of the stack as a prefix, I think. Yeah, I think that's the case, which makes it why that this is strictly increasing. We can actually play around with this. I think, like, to be honest, if I was in a contest, I probably would submit it because a 5-minute penalty is probably worth doing it. But I want to just print out real quick. Print, let's see, x and down of oh, this is terrible. Let's call it, I don't know, item for item in answer, or not answer, stack. Make this a tuple, and then we have to make this a list. I think I did the length the other way, but this looks like what we said is true, which is that this should be strictly decreasing. Oh, sorry, this is the answer will be strictly increasing for the length, because you know, you always take, like, for example, in this case, you would always take, if you would always take the 5, you would take the 5. If you cannot, then you take the 10 for the same length, but you would never want to take the 10 over the 5, and because this is because the length is monotonically increasing, that should be an invariant in the problem as well. Okay, I think I'm convinced. Let's give it a submit. Watch I be wrong about it after all that. I think I clicked on submit. Okay, yeah, there we go. Oh no, wrong answer by a lot, actually. Maybe I was wrong about the invariant. Let's give a look. No, that invariant holds. So I just have, oh no, this is wrong. Dun dun dun. So maybe not. So that invariant doesn't hold, which is what I was worried about. So we have to make some modification to this to get the proper answer. So if this is going down, what does that mean, right? If this is a smaller number, well, I think I'm just trying to think whether or when does it make sense to push this. Maybe it doesn't make sense to push this, and that's why we're getting the wrong answer. Because for every number that is, I think, yeah, maybe I have to ask myself. I wasn't sure, but I think as part of the stack, we have to ask ourselves, right? Okay, for example, we have a new number coming through. You know, let's actually copy and paste this real quick. This is kind of a tricky problem, but let's copy and paste it here. You know, let's say we have this, right? And we ask ourselves the question, right? Let's say we have, I don't know, a smaller number. Let's say 1. We have, the next number is 1 going in, right? What does that mean? Well, if this is a 1, we don't want to put this in if this is a 1, we never want to use this number anyway because we can get better results here. If this is small, if this is bigger than a 1, so if this is a 3, say, we also don't want to use this number because, well, it's not relevant to this number. So I think now we just have to, maybe from that invariant that we try to figure out, we have to actually check that the number that we're inserting has a bigger strict value. So then here we're keeping that invariant that when we insert a number or we insert a sequence, we make sure that that's that the number we give a longer sequence as well. So let's try that. It's only a hypothesis, but yeah. So the index, we keep track of the index, which is why we have to do this mapping here. So instead, how do we check? Okay, so I guess this is the score. I guess score is the last ends down. So we know that from here that we popped everything that's already smaller than it. So now we just have to kind of keep doing this as well, or we just have to check that if this is greater than or I guess equal to, just in case. I think equal to is okay. If this is go to, then we get to push this. Otherwise, then we just kind of ignore pushing it on the stack. Okay, I think I could buy that. Or if length of the bigger stack is 0, I guess. And then we have to do something similar on this side. But before that, let's see if it gives us a better answer. It should still give us the wrong answer, unless we're really lucky. But it should give us an answer that's bigger than 30 in either case. I guess not. Well, I mean, this is also a possibility that it just doesn't change the answer because it happens on the other stack. So okay, so let's also put this here then, just for symmetry's sake, and also that it would be more correct. Yeah. Hmm. 57. So this is definitely the improvement that we're looking for, but it's still clearly not the right answer. That's not great. Did I mix up the stacks? No, it seems okay. Let's also print out the smaller stack. Is this entire? No, it's not the entire number list. I was wondering if it was just one of those things. Mistakes were made. Should have gone to sleep a little bit earlier and do this with a fresh mind. I mean, this looks like it makes sense to me. If it's a bigger number, then it would take. It wouldn't make sense to take any of the other smaller ones. Okay. Why is it 50? Why is it 67 then? Dun dun dun. Oops. Oh no, did I lose the test case? Oh no. I think it's on the paste. So. Nope. Oh, I guess I could just go back and then copy in this. And I should have just done it the n square way. It would have been much faster. But I... So I was wrong about my invariance. And that is sometimes just the thing with greedy problems, is that you're wrong with the greedy. Suppose this 15. How does this even work? I guess let's print out both, maybe. Oops. What does this tag represent anymore? Oh yeah, these are just numbers. So 0, 100, 1. I don't even see the... Oh, there's the 100, but... Oh, I think that is... I have a maybe logic error here. I think that's why. I was wondering why... So the question is, I was wondering why 100 is here. And I think what happens is that... you know, when the 100 came up, which is, I don't know where... Oh, here, say... It cleared up all these numbers, right? Which is not great because we want to consider, you know... We want to consider these other numbers. And popping all of these is not good because... So one of the invariants that I was wrong about, at least for the longest path, is that... yeah, we're looking for a bigger number, but we also want to consider not just the biggest, a possible bigger number, but a number that allow us the longest sequence, right? Because let's say, you know, this 57, I guess, comes in later, we want to be able to use some of these other numbers. So I think that's the part that I messed up. And then the question is, how do I fix this? At least in linear time. Because now, another way to think about it is that the 100 is still a candidate for a new sequence, but so is, you know, 76, for example. Because you can imagine that, you know, you have a 100 and then like 99, 90, you know, keep on going 99, 100, 99, 100, and so forth. And, you know, you would never go back to 76, so that it does become bigger. And I'm too tired for this, as you can kind of see my eyes. Well, this is a problem that mono stack is not the issue. Sorry, fam, that I'm struggling a bit. No, it does find a way, but I think it does destroy some of the lookups, which is why it gives us the wrong answer. Yeah, I mean, during the contest, I definitely would have done the n square way, but why is this 2? Oh, I guess it's just one direction. Okay. like this 12-3, we give it up on it way too quickly, right? Because, you know, oh, somehow that was right actually, but that's because it's, yeah, but there's some interaction between the up and the down that I thought would be independent, but maybe there's some interaction there. Sorry, fam. I have to think about this a bit. The core part is that I'm trying to think about how this interacts. Do we always want the longest sequence that fits? If so, then what happens to this 101, right? Because let's say, I think the core problem is, let's say you have these two candidates and the next number is a 50. Well, if the next number is a 50, this was, I think this was, I took it for granted a little bit in my invariant earlier, because I think I was solving it for kind of a different problem, because I didn't get the longest length part. But let's say that's your stack, if you will. And that's a valid, or that should be a valid stack, because let's say you have a 50, 50, the next number is 50, right? Well, in theory, the 50 could, match here to continue this length, but it could also match the 100 to continue, and we have to make that decision, and it could go either way. It's not super clear that you would have it one way or the other in terms of decisions. And also the answer is, obviously if you have, say, 80 is the next number, well then what do you do, right? Do you still, like, do you consider, maybe, or even a better example, slightly better example, next number is 99, right? Well, not any of these will not be considered, and then it'll be 100 is the one that gets considered as the next possible answer. So we can't throw away the 100 either, is what I'm saying. I don't know. Now I'm not so sure that I can do it. Well, not. I mean, maybe it can be done in linear time, but I'm not sure I can do it in linear time. Because anytime you have two decisions, then it becomes a little bit awkward. Because like you can think about another case where, let's say this is, I don't know, 20, and then you have 120 and then 10, right? Well, if you have a number that's incoming, how do you decide between which three, right? So then now you have these decisions where even if you have greedy, you have to choose between them in a sorted kind of way, which is at best n log n if you do something like that. So I'm missing one observation that makes greedy work, I suppose. Besides that, I have to take advantage of the nums as less than 1,000, and this linear time thing is kind of bull. And So yeah, you can see that even I get stuck on these problems. Okay, I think I have another way of doing this with dynamic programming. Actually, now that I think about it, okay, that's. Whew. This is why greedy is tough, because you can you can get the wrong answer no matter what. Okay. I think an observation that you can make is that, let's say, let's say you have an increasing sequence. Let's say you have this number, right? So in a way of increasing sequences, you basically only keep 2 of these, right? So basically, yeah, and you can, yeah, maybe this is a little bit better. But yeah, one way to think about this is that, okay, let's say you have an increasing sequence. For every chunk of increasing sequences, you only keep 2, right? So I think that's the way that I would think about the recurrence. Because I think initially my n squared naive solution is that, okay, and this is actually, this is the increasing sequence. My initial n squared solution is that, okay, for 5, let's keep on going to find, bigger numbers or whatever, all the way to the end of the list, and then that's going to be n squared. But it turns out that probably you just have to look at, in this case, the 15, because this is, this is all going to, at least if you're looking for an increasing, because the 10 and the 13 and the 15, it doesn't matter, right? Because the 10 and the 13, it doesn't matter, because you're basically compressing them. So basically, we're just we can save the work by looking at adjacent elements. So I think that's the big observation that I missed for a long time. So let's kind of get back to it. So then basically now we have 2 sequences that we can do, right? So let's say find increasing, maybe index. So if index is equal to n, let's say n is equal to length of nums. This is actually, for me, going to be similar to buying stock with a, buying and selling stock dynamic programming. So I basically have to find an increasing, which is find the longest increasing the longest Wiggles subsequence where next direction is increasing, right? So yeah, otherwise and we can yeah, we might have to play around with the numbers here. So that we have a base case. But yeah, if index is equal to 0, well, then let's just return 1 plus find increasing of index plus 1. And this is just, yeah. Okay. This is just a base case. If index is equal or is greater than 0, so else we want to, if the numbers of index is greater than or equal to, because if it's equal to, then we compress it anyway. If you go index minus 1, then we return find increasing of index plus 1. Yeah. Else we return 1 plus find decreasing index plus 1, right? And we can also, in a similar way, do the same thing for find decreasing, right? And the reason here is that if the two numbers that are if the next number or if this current number is bigger than or equal to the next number, the previous number, then you the idea to think about is that now you're compressing them into one, and you're not counting the extra one. And here, if the opposite, then you would find 1 plus to find decreasing. That's basically the idea. Like now you compress them to one number, and now you start the beginning of a decreasing in this number. So that's basically the idea. Yeah, and you can probably guess that this find decreasing part is going to be very symmetric as a result. Yeah. And yeah, actually, I was gonna say, I don't know that there are any subproblems. So now we just find max of find increasing of 0 and find decreasing of from index 0. Maybe this is enough. We'll see. Okay. Usually I would say that you can take advantage of subproblems so that you cache the results, but I think this is totally deterministic, and you don't do any branch outs, right? So I don't think there is anything to take advantage of. Let's give it a quick submit. Cool. So you don't even need this. I mean, I was gonna say it's dynamic programming because I was, going in, I was trying to phrase this in a way such that, I can, do a recursion. But now that I think about it, I guess I don't really have to. Cool. And this is going to be linear time because, yeah, like literally all of these are just go to index +1, and then or if you want to think about it in dynamic programming, index has n possible inputs, and each does over one work, and we don't even have to cache, right? It just goes to the next one. So this is O of n times, I think. That'd be funny if I'm wrong. No, I mean, we don't do any branching, so it's going to be, yeah, this is O of n time, and this is O of n space due to stack space. And you could actually convert this to a for loop now that I have it this cleanly, and it should be okay. Cool. I'm not going to explain this too much more because I'm going to re-record this video has gone too long, so I'm going to re-record this the explanation in the beginning. So if you're watching this now, the explanation is actually in the beginning because this has, for longer videos, this is what I do. And if you're watching here, that's all I have. Thanks for watching. Thanks for stopping by. Hit the like button, hit the subscribe button, join me in Discord. Have a great night. I'm going to sleep really well at some point. And yeah, stay good, stay well, and to good mental health. I'll see you later. Bye-bye.